Hello everyone. Today we are going to talk about Chapter 8, Earth as a Planet. Because Earth is our home planet, we'll first talk about the Earth and later on we'll talk about other planets. You can see this is the image of the Earth and was taken by Apollo 17 astronaut. It looks very beautiful and the name of the image is called Blue Marble. First of all, let's take a look at the global perspective of Earth. You may already learn a little bit about Earth from previous chapter, that Earth is one of the terrestrial planets, so therefore it's actually made from rocky material, or more precisely that the surface of the Earth is made from rocky material. And if you look at the overall property of the Earth semi-major axis, basically how far away from the sun on average is about 1 AU. That is how the AU determined by, if you still remember. The period is 1 Earth year, and this is the mass of the Earth. You know Earth is not the smallest, it's not the largest planet in the solar system. By the way, in terms of Earth's distance from the sun, Earth is further away from the sun than Mercury and Venus. And you can see here's a way we can measure diameter radius of the Earth. And the escape speed is basically how fast the object needs to travel in order to escape Earth's gravitational pull, like altogether. And the rotation period is roughly a day. And we'll already talk about density and the air pressure and the surface of Earth. You can, doing the calculation, use a formula. And we as a creature living on the surface of the Earth, it is easy for us to explore around how the surface structure looks like. However, and it's really we have very limited tool to actually go deep into the interior of the Earth. So therefore, the interior composition and the structure of the Earth are actually probed using the seismic wave. Seismic wave is actually a wave produced during earthquake. Because a wave will travel differently through different materials, so therefore, by looking at how the seismic wave travel at different regions of interior Earth, we can get the structure and the composition. And you can see, so overall speaking, the Earth has on the very top, we have a crust. Right underneath crust, we have mantle. And close to the center, we have two-part core. We have outer core, which is marked by this red region, and we have inner core. And in terms of a material, we know that the crust consists primarily of oceanic basalt and continental granite. And underneath the crust, the mantle, you probably know that sometimes we will get some like sample or material from mantle from the volcanic eruption. And you can know that those magma or lava flow out from volcanic eruption is also rocky material. So mantle is also made from primarily rocky material, but because within the Earth, the mantle is actually with pretty high temperature, so most of rocky material is actually in the molten state, which is magma. And if we go even to the center, we have a core. If you still remembered, we talked about Earth's density is actually much higher than the average density of rocky material. So that indicates the Earth actually have a core made from metal. It's most likely made from iron. So Earth have an iron core. And because you can imagine, the mantle is already very hot. The core of the Earth is even hotter. So even the metallic material like iron will be a molten state. So iron will be a liquid in the very center of the Earth in the core. And if you also remembered, Earth also spinning around its own axis. The rotational or spinning period is about 1 day. Because iron is a good conductor, and together with Earth's spinning, will create kind of the moving of electrons or charged particle that resemble the current. As a result, if you learn some physics, actually the current can produce what we call magnetic field. Therefore, due to the liquid iron core and together with the spinning, the Earth actually have a global magnetic field. And this magnetic field not only covers the surface of the Earth, but is actually extended into a region actually surrounding us. This region influenced by the Earth's magnetic field we actually call it magnetosphere. And this magnetosphere can trap charged atoms or particles actually coming from the space. You can see that the sun actually emits the sunlight. At the same time, the sun also blows what we call the solar wind. The solar wind actually brings in a lot of charged particles and to the direction of the Earth. So you can imagine that it's like the wind always blow from the direction of the sun. So as a result, Earth's magnetosphere is not a perfect circle, and it actually like stretched in the direction away from the sun due to the solar wind. And the solar wind actually also bring a lot of charged particle within it. And however, the charged particle actually have a lot of radiation. And however, the Earth's magnetic field were able to trap the charged particles. So most of the charged particles are trapped, what we call in this Van Allen belts. Most of them were kind of stopped away from the Earth. Only a few of them were able to enter the Earth. For example, if you're looking at near the North Pole, which is South Magnetic Pole, and the south near like Australia and New Zealand, those are North Magnetic Pole. That is a place where those charged particles can enter Earth's atmosphere, therefore interact with the air molecule in Earth's atmosphere, produce a very phenomenal or very beautiful phenomena we call northern light, or sometimes we call it aurora. Now I want to share with you a video on how the magnetic field of the Earth can trap charged particles.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here we're going to start turning it up, and you can see it's starting to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. So if I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion going right back to where it started. And if I turn the magnetic field back down to 0, straight again. So there's direct visualization of the circular motion of charge in a magnetic field.
You can see clearly from this picture, you can see all the charged particle actually from the solar wind. Before it can reach the surface of Earth, it will start to rotate, form a circle around the magnetic field lines. So all the charged particle will kind of orbiting around the magnetic field lines. So most of them will be shielded away from the Earth. Now I want to share with you another video which is very beautiful northern lights, sometimes we call aurora. As we talk about, those charged particles actually have a chance to escape when the magnetic field lines actually intersect with Earth's surface. So those charged particles interact with air molecule, actually produce a very beautiful northern light. You can also observe this similar phenomenon near the other pole of the Earth's magnetic field, which nears Australia or New Zealand, and sometimes we call it the Southern Light. I will stop here, and you definitely can find a lot of Northern Lights videos with very relaxing music. And you can see the Northern Light can be different color. It's because charged particle will interact with different kind of gas molecule, so it will actually able to produce different colors. If you look at, the Earth as a global perspective, you can see, at least from this image, the thickness of a crust compared to other part of the Earth is actually very, very thin. So you, as a creature only live on the surface, you may see there is a lot of variation of a height on the surface. If they are scaled, even the highest mountain on the surface of the Earth, for example, the Mountain Everest, is less than 10 kilometers high. So therefore, compared to Earth's radius, it's actually very, very small fraction. So if the Earth or the surface feature on the crust, if they were scaled on the Earth, would be unnoticeable. And if, in fact, if the Earth were the size of a bowling ball, the surface would be as smooth as a bowling ball, even when we're considering the height of tallest mountain and deepest ocean. Next, let's look at a little bit more detail on Earth's crust, because that is a part we actually living on, and we actually have a lot of observation, and we actually know a lot of information of the Earth's crust. So first of all, you may already know that Earth's crust is primarily made from rock. So the terrestrial rocks, they can be classified as 4 different types. The first one is igneous rock. And this kind of rock is cut from the molten states. So for example, if you have a lava come from the volcanism and flow on the surface on the crust and then solidified, and that is igneous rock. And therefore all volcanically produced rock is igneous. There are also two other kind of rocks, like a sedimentary rock or metamorphic rocks. These rocks are familiar to us on the Earth. But it actually turns out those rocks are not common on other planets. And because you will later learn that these rocks actually have a little bit complicated process that only happens on the Earth, the procedure could produce those two types of rocks. Sedimentary rocks are made from the fragment of igneous rock, as all the shells of living organisms deposited by wind or water and cemented together without melting. So you can imagine in the sedimentary rocks, we were able to find a lot of evidence of ancient life, or you can see the fossils. A metamorphic rock are produced on Earth because of this active geological activity. They carry the surface rock down all the way to the considerable depths and brings them back to the surface. So you can imagine without such geological activity, this change of rocks would not exist at the surface. And the fourth very important category of rocks, we call it primitive rock. So actually, what is a primitive rock? That actually can tell us much more about the early history of the planetary system. This type of rock, which largely escaped the chemical modification by heating and the geological activity. And those primitive rock actually represents the original material out of which the planetary system was made. So primitive rock will be the oldest rock we can find on the Earth. But you can see because the Earth is so active, we barely have any left. But sometimes, if we are lucky enough, we'll have some gifts of primitive rock from space. The meteorites sometimes are coming from the meteor, and those sometimes they are still primitive rocks. They still are the rock from the beginning of the formation of the solar system. On this rocky Earth's crust surface, our planet is actually very active. Earth's crust is one of the most active surfaces in the solar system for all the planets. And our planet's geology is dominated by the plate tectonics. So basically, that the whole surface or whole crust actually composed of different crustal plates. They actually move slowly in response to the mantle convection. So let's explain a little bit what is convection and why the plates actually can move. The phenomenon of convection just means the hot material raise up and the cold material sink down. I actually want to show you a very interesting video demonstrates the convection. You can see here from this image that you know that hot material, in this case is hot water wants to stay up and cold water want to stay down. So if you put a hot on the top and a cold water at the bottom, there's no current, they won't move because they're already in the place they want. However, if you flip it, put cold water on top and hot water at the bottom, hot water wants to go up and cold water wants to go down. As a result, it is actually form what we call the convection current. So you can see this time the color, the blue and yellow color start to mix very well. When material become hotter, it actually expand a little bit. As they expand in volume, their density actually become smaller. As the density becomes smaller, the smaller density want to float, and the cold water still have a larger density, so it won't actually sink down. So therefore, it actually have something to do with the density. And so we'll apply this concept of convection to look at the Earth's interior. If you look at Earth's interior, we're not going to touch outer core, inner core, we'll only look at the mantle. Go all the way from Earth's surface, Earth's crust, go down to the mantle. The temperature actually has become hotter and hotter. You can imagine near the bottom of the mantle, the temperature of those magma is very, very hot. Remember, convection is that hot material wants move up. And you can imagine when this magma, which is a liquid rocky material, when they move up, they will go into the environment that cooler and cooler when it gets closer to the surface. So therefore, when they move up and spend some time on top near the crust, on top of the mantle, the temperature actually become lower. As they become cooler, remember convection is cool material wants to go down, so therefore they actually move down all the way to a little bit inner or deeper part of the mantle. And as a result, this flow of magma from the deep part of mantle or the part of mantle close to the surface, what we call actually form this magma current. So you can see they actually follow a certain direction. Remember, those are all our molten material like liquid magmas, and Earth's solid crust is actually sitting on the molten or liquid magma. It's just like a boat sitting on a river, a liquid water. So what happens? The boat will actually drift with the river. For example, if the river is go all the way downstream, the boat, even without like a manpower or motor, the boat will drift with the current of underneath liquid, which is the same idea as Earth, the plates, the crust, the possible crust will kind of drift together. It's driven by the mantle's convection, kind of follow the direction of convection current go. So for example, if underneath the crust, the convection current is go to the left, the plates, the crustal plate will also move to the left. And underneath Earth's crust, different part of the mantle actually have different direction of convection current. So you can see there's different plates. The movement of plates are all different. So you can see there are basically 4 basic kinds of interaction. So you can see some of them, the plates are pulling apart at their boundaries. And also, and there's a plates, they can kind of push against each other, right? Their plates push against each other. And the third one, And there's also plates. For example, an example is near North American plates. And you can see near the west coast of North America, they can actually slide alongside each other. And for the plates that are actually and move towards each other, there are basically two kind of effects. It's one that one plate can go underneath the other plates, or the other case is you probably heard about the mountain Everest or Himalayas mountain actually form is one the plates actually jam together. And we believe this continental drift is still going on and it's already happened a long time ago. You can see this simulation give an idea and how the continental drift over the last very long time. And you may have heard about the reason why actually scientists realize that the continents may be one part or may drift from a long time ago is that if they match South American with African plates, looks like they have a great match. And when they found some creatures and the continents or islands now is far away from each other, but they actually share some of the type of animals or the living creatures. So that's also the evidence there. They used to be one big continent. Now let's look at this tectonic activity will produce what kind of feature on the surface of Earth or result what kind of events on the surface of the Earth. And they include, of course, we already talked about the first is continental drift, and the also recycling of the ocean floor. We'll talk about in more detail when we talk about the rifts. And the mountain buildings, the two plates, they jam together and they keep rising in terms of height. And the rift zone, and we'll talk about that, is actually creates when the two plates are moving away from each other. And subduction zone is the one plate is going under the other plate. As well as a fault. The fault is produced due to two plates slide along each other. And we also have a lot of instability along this active region on the Earth. For example, earthquake, volcanic eruption of the lava from interior. And let's first look at the rift zone. The rift zone actually created two plates kind of moving away from each other or pull apart from each other. And you can imagine when the two plates pull apart from each other, they will left a gap in between, right? However, if there's nothing underneath, we probably will get a valley. But remember, if there's a tear or a gap on the crust, what happens? All the magma from the mantle will start to wells up. And when the magma come from mantle wells up, they will meet the cold ocean water, they will solidify. So as a result, they actually will result a little bit higher up structure we call the rift when the plates are actually pulling away from each other. Because this molten rock rises from below to fill the space between the receding plates. And one of the most famous one is the Middle Atlantic Ridge, which is a rift. And near the rift zone, you can imagine because there's like a lot of tiered part or like a gap, there's our active volcanism near the rift zone. And another or explain in a little bit detail is subduction zone. The subduction zone happens when the two plates actually kind of move towards each other. And in this case, is that one are thicker continent plates meet with a thinner oceanic plates, because the thinner oceanic plates were able to move underneath this thicker continental mass or plates. So therefore, you can see as a result of the two plates move towards each other, the oceanic plates will go under. As these oceanic plates go under and deeper, you may know that the part of mantle is actually very hot. So all the material used to be the oceanic crust plates are actually start to melt. So that's a way we call it the recycling of the ocean floor. And usually the amount of recycling or the part of the subduction zone being melt, usually it's comparable to the ocean floor generated by this the two plates moving around apart from each other. Again, near the subduction zone, there's a very active volcanism can happen, as well as earthquake, because the plates is not stable, especially for subduction zone. There's a lot of stress can create it under the process. And a third one is when the plates actually slide along each other, slide against each other along the way. They actually not move towards or away from each other, but they move towards a different direction, slide against each other. And when the two plates, you can see, of course, clearly when the plates slide against each other, slide alongside each other, there can be a tear on the crust or on the surface created, which we call fault. The fault in California is actually lines and the boundary between the Pacific plate and the North American plate. Unfortunately, the motion along the fault zone usually does not take place smoothly because there's a lot of frictions. And so this creeping motion of the plates against each other therefore build up some stress in crust, and they are released in a sudden violent way that basically generate earthquake. That is one of the reasons California usually have a lot of earthquake compared to other part of US. And finally, that when the two continent mass, we're talking about when the two continent mass, when they are both thick, none of them will go under the other to form a subduction zone. So what happens, they will basically collide. They will push against each other under very large pressure. For example, the mountain Everest was formed by this force. If you look at the location of Mountain Everest, it's right kind of at the boundary of the Indian plates and Eurasia plates. So the plates jam against each other actually creates the Mountain Everest. However, this plate tectonic or the continent plates push against each other generate just the rise, the overall height. But you looking at the very top of the mountain, you can see the top of mountain is actually thinner, right? Compared to the bottom. And once a mountain actually formed by this upthrusting crust, the rock actually subject to the erosion by water and ice. You can see this part, this valley, actually eroded by glacier of this mountain. So the mountain first rising up by plate tectonics and then shaped by the erosion of water and ice. Next, let's move towards the other direction. Let's look up from the crust. Let's look at Earth's atmosphere. So Earth you probably already know that Earth's atmosphere is composed primarily from nitrogen, which taking about 78%, and oxygen, which is essential for our life, about 21%. And the rest of 1% of the Earth's atmosphere actually have the water vapor, H2O, carbon dioxide, and ozone. And also we have some other very small amount of other gas not listed right here. And if we look at the overall, the atmospheric structure from the surface of Earth. So the closest part, the layer close to the surface is the troposphere. The troposphere is where the convection happen, and all the weather events are all kind of within the troposphere. And you can see the clouds pretty much mark the top of troposphere. And convection is also play a big role for a lot of kind of weathers. You may learn about water cycle. When the water actually evaporate from a hot surface, when it go higher and higher, you can see here the red curve is actually marked as the temperature. You can see when it go higher and higher in the troposphere, it gets colder. So therefore the water vapor actually condensed to form a clouds. Then the clouds actually, when the clouds have no longer able to hold all the water droplet, will start to have a rain or snow, depends on the surface temperature. And so all the weather events all happens in troposphere. If we go up the clouds, we are get into the stratosphere. Stratosphere actually have very stable flow of air. So therefore, that is a perfect place for the airplane to fly. If you have experience taking the airplane, once takeoff, the airplane is not very stable, right? Because it have to go through the troposphere, and troposphere have a lot of movement of the air, and the airplane it needs to go all the way above the cloud, go into the stratosphere, so where it has a very stable flow of air, so it's actually safer for the flight. And near the top of stratosphere, we have ozone layer, which is ozone is actually 3 oxygen atom. The ozone layer actually helping us block most of high energetic radiation such as gamma ray, X-ray, and ultraviolet. And above the ozone layer, we have mesosphere, and finally we have ionosphere. And if you take a look at the change of temperature curve along here, you can see the temperature is not always decreasing or increasing. Within the troposphere, the higher you get, the colder you get. However, when you go to stratosphere, the temperature actually becomes a little bit stable until you go all the way to the mesosphere and to the ionosphere, and the temperature start to rising again. We believe the ionosphere and the mesosphere has higher increase in temperature here is due to the heating from a high energetic radiation from space. And the troposphere, the bottom one troposphere, where we have greenhouse effect, basically trap a lot of infrared radiation near the surface. So we actually therefore have a little bit higher temperature compared to the other part. And you can see, although this is the structure of the atmosphere of the Earth, the mass of the air is not evenly distributed. Within just a 5 kilometer, basically this like this line, half of the air atmosphere is actually concentrated under the 5 kilometer. If we go all the way to 10 kilometer, 90% of our atmosphere is actually below this level because as well as other object has mass, they are subject to gravity. The air, although is much less denser, but it also has mass. So they also subject to the force of gravity of the earth. So they all concentrate actually very close to the surface. Therefore, if you climb to top of a mountain or even take a rocket ship, you have to go to the higher elevation. You have to make sure you bring the oxygen tank with you or have a supply of oxygen because as you go travel up and up, you basically in a region with much less amount of air for people to breathe. In terms of 13 kilometer, 99% of air is below 13 kilometer. So you can imagine the above 13 kilometer, although it's still a part of the atmosphere, but they actually have a very small amount of air within those layers. And you may also notice that the atmosphere or air, they are not really stay at stationary, right? So there is always air circulation. If there's a local circulation, you can feel like as a wind. We already talked about convection is another force make air to circulate from bottom to a higher place and from higher place come back to the bottom. And atmospheric circulation and typically bring us the weather. It is actually driven by the seasonal change of deposition of sunlight. So you know that part of Earth may receive more sunlight and part of Earth not a lot of sunlight, and air circulation actually can even up the heat. Therefore, and to redistribute the heat along the surface of the Earth. But can also result a catastrophic events such as a hurricane. Now I want to share with you a short video to describe those catastrophic weather phenomena due to the air circulation and the redistribution of heat from the sunlight.
Cyclone, typhoon, hurricane. All of these names are used around the world to describe the most powerful storm known to man. Hurricanes are unpredictable, but scientists have a thorough understanding of how hurricanes form and sustain their power. In the Atlantic Ocean, hurricane season peaks during the late summer months when tropical waters are the warmest. Hurricanes form from a cluster of thunderstorms that suck up the warm, moist air and move it high into Earth's atmosphere. The warm air is then converted into energy that powers the hurricane's circular winds. These winds spin around a low-pressure center called the eye, which can provide a 20 to 30-mile radius of eerie calm. Encircling it is the eye wall, a towering ring of clouds with some of the fastest wind speeds of the hurricane. Surrounding the eye wall are curved bands of clouds, the rain bands, often tens of miles wide, releasing sheets of rain and sometimes tornadoes. When a tropical storm's winds reach at least 74 miles per hour, it becomes a hurricane. The hurricane then receives a category ranking of 1 to 5 on the Saffir-Simpson scale, based on its wind speed and potential damage.
You can see that's pretty much how the hurricane forms. Now let's talk about how the Earth actually become what we experience today. Actually, at the very beginning of the Earth, like when the Earth was first formed, it is not a habitable place. They have a heavy bombardment and the environment is not comfortable at all. So let's look at how the life and the chemical evolution of the Earth, as well as how the Earth's climate change, so will lead to the Earth to be a comfortable place at this moment. I would like to say that one of the most special thing about the Earth is actually we have life on Earth. And life is actually originated on Earth at a time when the atmosphere is lack of oxygen and consists most of carbon dioxide. You may still remember the Earth's atmosphere have carbon dioxide, now it's just a very small amount, and the nitrogen. We believe our nitrogen and carbon dioxide are mostly come from the geological activity, like volcanism brings some gas actually dip from the mantle to the atmosphere. According to the chemical evidence, we're actually looking at the oldest surviving rocks were formed 3.9 billion years ago. Life already exists. And the life had archived sophistication to build a large colony we called stromatolites. And the stromatolites just a layer of sedimentary rocks or formation that created mining by the photosynthesis microorganism, mostly like photosynthesis bacteria. Of the photosynthesis bacteria, or later on we know that the development of blue-green algae, they can actually take into carbon dioxide and convert that into oxygen and release to the environment. So from that time, due to the photosynthesis, we actually have decreasing of carbon dioxide level and increase of oxygen. As the free oxygen began to accumulate in the atmosphere about 2 billion years ago, and this actually leads to the formation of Earth's ozone layer. Remember, the ozone layer is actually, instead of 2 oxygen atoms, it actually has 3 oxygen atoms. So this actually protects the surface from the very high energetic solar ultraviolet light, X-ray, and gamma ray. So therefore, they actually give a chance for the living creatures to move away from the ocean because now the ozone layer already protect them, so they were able to survive on the continent and outside of the ocean. And at the same time, the increase of the oxygen and actually promote or make it possible to the appearance of animals. The animals able to breathe directly from the air of the oxygen, at the same time consume the organic material produced by the plants as their food. So for example, if you're thinking about the human beings, although we now have a variety of food, but if you trace all kind of food we eat, they all trace back to the plants. For example, the meat we eat is actually the animals eat the plants, like grow in size. Of course, like the rice, the flour we eat are all traced back to plant. Even the most processed food you can buy from grocery store, if you trace them back, they are all from plants. So even if the human being has very high advanced technology, but the basic survival needs, the food we eat are still just from the plants, the other lives on the earth. So you can imagine the animals won't appear until the earth is actually populated by the other like creature like plants, bacteria, and when the earth's atmosphere start to accumulate a lot of oxygen for animal to breathe. So if you look at the tree of life, we actually all originate from the common ancestor. Although we have a wide diversity of species on the planet, but we actually are related to each other very closely. For example, human is a type of animal. We actually have very close relationship with chimpanzee, which we have in terms of genetic level, we actually have a similar, like 99% similarity in genomic level. So you can see the appeal of animals or human being, the reason why we are here, Earth is a very comfortable place to live, is due to their life, right? Because life produces food for human being, as actually, especially the photosynthesis plants generate the oxygen and on the surface of Earth, which is essential for human to survive. In terms of climate change, and you may heard about carbon dioxide and methane. There's another small amount of gas in the atmosphere. Sometimes we call this greenhouse gas. So they're actually able to heat the surface through the greenhouse effects. Let's briefly explain what is greenhouse effects. Then we'll take a look at the simulation and how the amount of greenhouse gas can increase or decrease greenhouse effects. The greenhouse effects is basically looks like this picture. So when the energy from the sunlight during the day absorbed by the surface of the earth, and the surface of the earth could radiate the heat during the night when there is no sunlight. However, the radiated heat from the surface won't be 100% go to the space. Instead, there is a certain percentage of the heat is actually kept near the surface. Only part of heat were able to go all the way to the space. And that is actually a good thing, because without the greenhouse effects, Earth will be too cold. Later on, you will learn about Mars. Mars is actually with much less greenhouse effects, so it's actually much colder. And the greenhouse gas, or sometimes the clouds, and it's just like a blanket we put during the night to keep the Earth's surface warm, so the surface temperature won't go too low when we don't have the heat from the sunlight directly. And you can imagine that on the Earth's surface, if we have no blanket, no greenhouse gas, we basically have no way to keep the heat closer, so we'll have very cold surface temperature. However, you can imagine if you have the blanket too thick, you can imagine that the Earth's surface will be too hot. So therefore, we really need greenhouse effects, but we just need greenhouse effect at a right level. And some other examples of greenhouse effect in our everyday life, like the name come from, like you know that in agriculture, they put plant in a greenhouse so it will keep them warm, right? And another example is that if you park your car outside a very long time, if you get in the car and at the first moment the car is very hot, is even hotter than the surrounding temperature or the outside temperature, is because the car, there's a lot of heat actually trapped inside the car, make it much hotter. Now let's take a look at a simulation of greenhouse effect. You can see when the sunlight strikes on the surface, the re-radiation, part of the re-radiation from the Earth's surface will be kept inside or closer to the surface. And you can see, therefore, kind of keep the temperature kind of stable in a certain level. So we'll manipulate the level of greenhouse gas a little bit. So for example, let's go to one extreme. One is no greenhouse gas. This is actually not a good thing, because Earth's surface temperature drop dramatically because all the thermal radiation from the surface of Earth all escape into space. So therefore, you can see the surface actually become very cold, right? And how about we go to the other extreme? If we have a lot of greenhouse effects or greenhouse gas concentration, you can see that most of the heat radiated from the surface will keep near the surface. As a result, the temperature will increase higher and higher. You may notice at the beginning, let's kind of redo this. At the beginning, the temperature increased very fast, right? So let's look at the greenhouse gas concentration historically. For example, like Ice Age. This is the Ice Age. Greenhouse gas concentration is not very high. So you can see the Earth have relatively low temperature. And in 1715, you can see this is kind of a level of greenhouse. And now in 2020, we actually have much more higher concentration of greenhouse gas. Actually, the majority of the carbon dioxide or greenhouse gas are produced by the industrialization of the human being after the Industrial Revolution, and instead of geological activity. The bad news is that on top of the industrial and agricultural development, and there's a widespread destruction of tropical forest, which basically get rid of a lot of plants actually able to extract carbon dioxide from atmosphere and produce with oxygen. Therefore, in the past century, the amount of carbon dioxide in the atmosphere is actually increased by 13%, and we are expecting it to continue to rise more than 0.5% every year. And that is actually what we call the global warming. You can see the science behind is actually pretty straightforward. As we have more carbon dioxide, we'll have a higher level of greenhouse effects. As a result, our planet will become warmer and warmer. And you can see clearly the evidence or data already show that we already have significant increase of amount of carbon dioxide in the atmosphere. So the increase of the overall temperature of global warming is actually inevitable. And around the world, and the temperature records are constantly set and broken. All but one of the hottest record year had taken place since 2000. There was a lot of bad things will happen if Earth become warmer and warmer. For example, glacier will retreat and the sea levels will rise, and a lot of cities close to the ocean will be underneath the water. And even bad thing is that we have no idea what time the level of carbon dioxide or the level of global warming will lead us to an unknown territory where we have no idea what's going to happen. And later on, when we talk about the planet Venus, that's an extreme example if there's too much greenhouse gas. So you basically, with increase of temperature, when the temperature is too high, you can see the water will evaporate. Basically, we're not going to have liquid water on the surface, and just as Venus. At the same time, make things even worse, the higher temperature will cook out, kind of burn more carbon dioxide from carbonated rocks, so will make the things even worse. So now I know the global leaders are actually working together to control the global warming rate and control the level of carbon dioxide we actually emit into the atmosphere. Because now is still a moment then As we work together, we can still control the level of global warming or climate change. If we keep dumping carbon dioxide into atmosphere or keeping cutting the trees or destruct of tropical or forest, and we actually bring us in a road we basically have no idea what's gonna happen later on. You can see, at least from this perspective, human activities can actually also influence dramatically the climate change. Now, human represents a dominant influence on our planet's atmosphere and ecology. You know that a lot of extinction of animals or creatures can link to the human activity. And we talked about the climate evolution already and the chemical and life evolution and how human activity actually influenced the Earth's evolution. And finally, let's talk about the cosmic influences on evolution of the Earth. That means any force actually come outside of Earth, actually how they shape the Earth. So cosmic influence, majority, we're talking about the collision of large asteroid or meteorite and on the Earth. And you probably learned that there was a lot of debris still left from the formation of the solar system, like those free rocks. There's the bigger ones we call asteroid, and the smaller ones we call meteors. And you may heard about there's a lot of meteor shower sometimes can happen. That is when these debris or rocks captured by the Earth's gravity. So it will kind of change its trajectory or path, and it will basically aim moving towards the Earth, and some of them will collide with the Earth. And we believe the Earth get most of the impact at a very early stage during the formation stage of the Earth or the solar system. Because at that time, the solar system is not very stable. There's a lot of debris like everywhere. For now, you know, a lot of debris are concentrated in like asteroids, in the asteroid belt between Mars and Jupiter. And also a lot of other debris is actually beyond the orbit of Neptune in the Kuiper belt and outer cloud. But at the early stage of the solar system, those debris is basically everywhere. That is the time we believe the Earth get most of the impact. And that at that time, because this bombardment is a lot of collision and impact, we believe at that moment Earth's environment is very hostile. The Earth must be very, very hot due to this impact, the heat generated from the impact. At that moment, you're probably able to see a lot of like craters, like the dent caused by the impact. But now if you look around the Earth, there is not a lot of the craters we're able to find on the Earth's surface of the Earth. But later on, if we look at the Mercury and the Moon, their surface is primarily covered by the craters. Can you think about why, although Earth still get a lot of impact at the beginning, why there is very, very, very few craters on the Earth? You may think about, we already talked about, there's Earth is actually have a very active surface. We have plate tectonics, right? And so the place is keeping drifting, is keeping changing. The surface is keep changing. So therefore, you can see a lot of surface the craters on the surface are already destroyed by the plate tectonics. And the other things, we have wind erosion and the water erosion. So the wind and the road can erode the structure of craters. And also the wind or water will bring in some more like mud or rocky material can fill up some of the crater. And in this picture, it's one of the most where preserve crater on the surface of Earth, at least it has some evidence that Earth experienced some of this impact during the past. But we cannot find a lot of craters due to the surface of Earth is very active. Most of the small debris, they will be burned out when they try to go through Earth's atmosphere. That's how you see the meteors. And for these very small things, when they landing on the Earth, they may only left a very small volume or mass, so they will see them as a meteorite. They won't make a big impact, won't be able to produce a big crater on the surface of the Earth. And of course, there is much severe impact in the past that can cause a severe consequence on the Earth. One example I'm going to talk a little bit about is some large past impacts actually lead into some mass extinction. You may heard about that the reason dinosaurs actually extinct is due to our like a large meteorite strike on the Earth. And based on the research, scientists actually know it's about 65 million years ago. And there's a large asteroid actually impacting on the Earth, and which wiped out the dinosaur and many other species. And the impact site is just located in Yucatan Peninsula and in the area near the seaside. So we call the Chicxulub crater. But nowadays, due to the Earth surface activity, we can no longer see the crater generated by the impact 65 million years ago. Now I want to share with you a video describe that big impact wiped the dinosaur off from the Earth.
The asteroid was 6 miles wide, weighing hundreds of billions of tons. Still, compared to Earth, it was tiny. How could it wreak such havoc? It would have hit at nearly 50,000 miles per hour. The energy released would be equal to about 100 million nuclear bombs. A huge mass of superheated debris would have been blasted into space, orbiting the Earth before raining back down. The Alvarezes thought the dust could have blocked out the sun for years, devastating life. This was the hypothesis for how the age of dinosaurs ended.
So you can see here, the main reason the dinosaur actually extinct is actually from the side effects of the impact of the asteroid. First, because asteroid is very big, it generates a lot of heat. So the surface of our Earth will become very hot. So dinosaur as an animal, they cannot sustain such a heat. And the second, the debris coming from, or the dust coming from the impact will cover the sky, so which will block a lot of sunlight for a very long time. You can know a lot of things or living things on Earth actually depends on the sunlight. So that's another reason there's a mass extinction happen due to the big impact 65 million years ago. However, although this is actually a very bad thing for dinosaurs, these big animals living on the Earth at that time. But we notice that by looking at the history of the life on the Earth, we notice that follow the mass extinction, there was always a sudden evolutionary burst as a lot of new species developed to fill the ecological niche opened by the events. For example, that is actually maybe the events give the mammal, the animals with a smaller size, a chance. And later on, the mammals actually able to dominate. So you can see we're actually luckily the beneficiary of this process, although it's very bad for dinosaur. So these catastrophic events can kind of speed up the evolution or to bring the evolution paths in towards different direction. You can imagine if there's no such impact happens, maybe the dinosaur still the dominant animal on the surface of Earth for nowadays. Of course, from our perspective for today, with a lot of advanced technology, we don't want the things happen to dinosaur also happen to us. Because imagine if we let this asteroid strike on the surface of Earth, even without our technology, as long as the impact happens, there's not a lot of things we can do, right? So we will become helpless. So, however, to prevent such things happen on human being, today astronomers actually are working on to predict or prevent or take action earlier before the next impact happen. So there is actually several small but very sophisticated wide field telescope are now used for the search for the asteroid that may heading towards the Earth. It is actually called the NASA Space Guard Survey Project. And in case we actually found that there is a large asteroid on the collision course with Earth, there were also other actions we can take. For example, the NASA also have a spacecraft called Double Asteroid Redirection Test. And this will basically try to redirect the path of asteroid, so to make it go away from a path that aim towards the Earth. This actually can be fulfilled by send some object to crash into the asteroid. So in a certain direction, already calculate good direction. So they will actually to change its orbit slightly, so the asteroid won't fly towards the Earth. So another action we can take if the asteroid is not too big, or if we discover the asteroid is actually on its way to the Earth, we can definitely bring some ballistic material. So this way we can destroy some small asteroids before it's actually reaching Earth's atmosphere or get close to the Earth. So you can see now with advanced technology, there's a lot of ways we can do our early detection and take action before any bad things can happen to prevent the similar large impact that wipe off the dinosaur. That is what I want to talk for chapter 8. In this chapter, we first talk about the global perspective. The interior of the Earth have a crust, mantle, outer core, and inner core, as well as Earth's magnetosphere. Then we talk about Earth's crust, the surface activity, the plate tectonics, what kind of structure are result from the plate tectonics. And follow that, we discuss Earth's atmosphere, what kind of composition of Earth's atmosphere, and what kind of layer we have inside Earth's atmosphere, and how the weather related to the atmospheric circulation. And finally, we actually talk about the life, chemical, and the climate evolution of the Earth, how that are affected by human actions, the life, as well as a cosmic influence.